Hello, and welcome to the i4Good Summit webinar series. My name is Andrea Manara from the ITU, the International Telecommunication Union. They have the privilege of introducing today's webinar. ITU is the United Nations Specialized Agency for ICTs, and we're also the organizers of the i4Good Global Summit, alongside the X Prize Foundation, in partnership with the 38 UN sister agency. The summit is co-convened with Switzerland. The goal of the summit is to identify practical application of AI to advance the Sustainable Development Goals, scale the solution to achieve global impact. We are pleased today to organize the second session of the workshop on satellite data analysis and machine learning classification with QGIS, in cooperation with the Politecnico di Milano and the UN Open GIS Initiative. We have a distinguished set of speakers, and they are also assistants by students, which are at your disposal should you have any issues in performing workshop activities. For this purpose, we will be using the Q&A functionalities, which you can find at the bottom of your screen. There is also the chat functionality. Please make sure to set the message recipient to all panelists and attendees, not just to all panelists. You can select this just above the message box. Without further ado, I'd like to introduce our speakers today. Maria Antonia Brovelli, Professor of Geographic Information Systems and Digital Mapping and Research Fellow Gorica Bratic from Politecnico di Milano. Over to you, Maria and Gorica.
Thank you. Thank you so much, Andrea. Thank you for giving us the opportunity of presenting this workshop. And good morning, good afternoon, good evening, good night to everyone. We know that there are attendees from all over the world, and we are very happy. We have known also that the previous workshop, so the part one of the workshop, was very well attended and very appreciated, and so we are very happy also for this one. And but before starting with the second part, I want to give the word to Gorica, who will alternate with me in the presentation of these workshops. So Gorica, welcome.
Thank you, Professor Brovelli. Hello, everyone, and welcome to this workshop, second part of it, actually. I hope you will learn a lot today, and we will immediately start with some things that we already seen in the first part. So just now, I will just, to make sure that everybody has everything ready for today, I will just quickly go through the important steps. So, the first step is to open QGIS, and in particular, to open it as, actually to open QGIS with GRASS, and to open it as administrator. This is important because run it as an administrator, because maybe we will have issues with the scikit-learn library in case we don't run it in this way. So again, QGIS desktop with GRASS, run as administrator. Okay, for me, it's already running. And now I will show you how to load the data, and in particular, how to load the data that we will use today. As the last time, we load data from the layer menu, add layer, and then first we will add vector data, so add vector layer. Layer, add vector layer. From here, we need to click on this three dots button in order to search our file system and find the data that we want to load into QGIS. In the case of the workshop for today, we only need ROI.shp. So these are the data that I provided you. You will find ROI.shp. So we select this one, and we click on open. And then we click on add. Now you can see that this layer is added to my QGIS. Then we will switch to the raster tab in order to add the raster files that we are going to use. So on the raster tab, again, we go to the three dots. And first raster that we want to add is the clip.tif, which is the output of the previous session. So either you got it from the previous session or you maybe downloaded the data that I provided specifically for today. In general, we need just this file, clip.tif. This is one file. So we select that one, we add it. And in the same way, we also add, again, we go on the three dots and we go to the GHS folder and we select all the files that are in the GHS folder. We click on open and add. And with this, we added all the files that are needed for today. Later on, we will explain what are they for, but just for now to have them all loaded so that we later don't spend time on this. And the last point that I want to recap is how to install plugin. Because today we need two plugins. So to install plugin, we go to plugins menu, manage and install plugins. And then we go to this tab all, and then we search for plugin name. The first plugin that we need is called classification tool. So we search for classification tool in the search bar. We select this one, jetsaka classification tool. And then here, if you didn't install it before, you will see install plugin. If you installed it before, you are fine, you don't have to repeat. And the second plugin that we need is Quick Map Service. Quick Map, okay, so this one. Quick Map Services, again, we click on install and we close. So now if you didn't manage to follow me, please, we provided the links to the slides, so you will have time to catch up. Now I will give back the word to Professor Brevelli to introduce you into some theoretical points. So in the meantime, you will manage to load all the data and all the plugins. So back to you, Professor Brevelli.
Thank you so much, Gorica. And yes, so this was a very super short introduction with something that we already saw last time. So we didn't spend so much time for this part because you are an expert if you attended the last part of the workshop, or if you watched at the video on YouTube. And before starting really with what we want to show you today, I want also to say hello to the students who are here as assistants for helping in answering the question. So please, if you want to show you up, Matilde, Juan Pablo, Thomas, Francesco, and Musa, thank you. These are all students of the Master of Science in Geoinformatics Engineering at the Politecnico di Milano. So they were my students because they already finished the course. And again, thank you for your very precious activity as you did last time. Your work was very, very well appreciated. So thank you. And then at this point, we can start the workshop of today. So I will share my screen. And today, what we want to do, because last time what we did was to prepare everything. So to prepare the image, in such a way to be able this time to classify it by using some artificial intelligence algorithm. We didn't spend so much words with respect to remote sensing because if you want to become an expert in remote sensing, there are specific courses taking a lot of hours, as a matter of fact. We didn't spend time also in telling what GIS are. Again, also in this case, the topic is very wide and you need many hours of course if you want to learn how to use completely GIS. And this time again, we will speak about some artificial intelligence, machine learning algorithm that, as a matter of fact, we won't enter into the detail. We will show you only how to use them in QGIS because the time is very strict, so we don't have time of entering into the details. Okay, what we want to show you today is how it is possible to do the supervised classification using QGIS and using specifically one plugin of QGIS. Just to give you an idea about what is the supervised classification, if you are not familiar with this, we can think about this example. Suppose to have some input raw data that in this case are pears, mangoes, and apples. You see here is my data set. And suppose that I have also some training data saying that if I find something of this kind, this is a mango. If I find something of this kind, this is a pear. I find something of this kind, this is an apple. And at this point, I have an algorithm which is able, if I run the algorithm, of subdividing my data in such a way to have the data of the class of apple, the data of the class of pears, the data of the class of mangoes. Okay, once I have the output, what I can do is to check, so to assess the quality of my classification. This activity is an activity that is called the validation. And the validation helps us in determining which is the accuracy of the classification that we made. So starting from this simple example, we will classify our data, our image, considering two different classes, the class of the built up and the class of non-built up. Obviously, this is an arbitrary choice, and you can classify data with the detail that you want, as a matter of fact, but we started with these two simple classes in such a way to make everything easier for you, especially if you are not an expert in this topic. For doing this classification, we will use, as Goritz already said, this jetsaka plugin of QGIS, and this jetsaka plugin of QGIS is helping us in classifying data considering three different algorithms: the Gaussian Mixture Model, GMM, the random forest, RF, and the key nearest neighbors, KNN. There is also another one, but we won't use the other one because it's not working well. Okay, so as we saw before in the picture, the first point is to have a training set. So the training set, this one, exactly this one, the training set saying this is a mango, this is a pear, this is an apple. And so the first point in our case is to create this training set. How it is possible to create this training set. So first of all, let us see in general what we do. And unfortunately, there is not a unique answer because there are not unique guidelines for deciding how to create the training set. So the creation of the training set, that means the size of the training set and where to choose the training sets depends strongly on the classification algorithm, the number of classes that you want to consider, the accuracy that you want to reach, and also by the budget that you have available, because we need to have very detailed, very accurate data if we want to do a good classification. So the main rule is to have the best available data in order to do the best classification. But obviously, for doing that, we need to make a great effort, and therefore very often we have to balance between the accuracy that we need in the end and the cost that we want to pay for having the best possible training data set. In general, there are some rule of thumb that are used for determining the size of the training set. And one possibility, but it's just one possibility, is to consider to have at least from 10 to 30 multiplied by p samples per class for training, where p is the number of bands used. But this is just one possible suggestion because there are other possibilities that are considered. And for obtaining this training sample, this training set, what we have to do, there are two main possibilities. One possibility is to collect the data in the field, so the in situ data collection, but obviously it depends where we need to classify the images and if it is possible for us to collect the data in the field or not. Another possibility is to use the photo interpretation, but in this case, to be sure that the images we are using are better than the image that we want to classify. So they are higher resolution with respect to the imagery that we want to classify. So for this case, we can use both very high resolution satellite imagery or also airplane imagery or also drone imagery and so on. So the two main possibilities are this one, collecting the data in the field, or doing photo interpretation, having higher resolution imagery. From the practical point of view, what we want to do is to create this training set. The creation of this training set is possible by using QGIS. So for doing so, we want, as a matter of fact, to create a layer, and therefore differently from before, because before we added a layer, so we selected layer and add a layer. On the opposite, now we want to create the layer, and therefore we select a layer as before, very intuitive, but then we select create the layer. And among the various possibilities, because you see that we have different possibilities, we decided to show you how to create a new shapefile layer. So the specific layer that we are creating is a shapefile layer. And the layer that we want to create is a layer of polygons, so a polygon shapefile, where we will describe polygons, where we'll create polygons corresponding to two classes, the class of the non-built-up and the class of the built-up. So again, when you will do that, go to layer, go to create layer, go to new shape file layer, and at this point you can start creating your layer. Please pay attention that in creating the layer, as jetsaka, the plugin that we are going to use later, is not accepting the value 0 for the class, we want to use this value. And this is the reason why we put here, you see that for the non-built up, we decided to use as identifier 1, and for built up, we decided to use as identifier the value 2. Okay, So at this point, once we have said to QGIS what we want to do, we have to add, first of all, which is the name of the file that we want to create. And we decided to call this file ROE, so region of interest. It means that here you will write ROE.shp, shapefile. And we want this file to be a polygonal file, so a file of polygons. And then the last point that we have to decide or to introduce is the projection we want to use, so the coordinate reference system we want to use. And we create it accordingly with the coordinate reference system of the Sentinel to image that we preprocessed last time. So by using these EPSG 32637. Okay, now this is complete and we can click on OK in such a way to create our file. Okay, once we have created the file, at this point, we want to start creating the polygons and start adding to these polygons the two properties. So the fact that this polygon belongs to the class of the non-built up or the class of built up. Okay, but before going here, I prefer to switch the word to Goritza in such a way that you try this first part of the exercise.
Okay, I'm sharing my screen. Okay. So we are supposed to now create one empty layer that later we will fill with the values, but for now we will go step by step. To create a new layer, as we saw before with Professor, we go to Layers menu, Create Layer, and then New Shape File Layer. Then here we need to define a couple of, let's say, properties of this layer. First one is file name, and file name is defined by clicking on this, again, 3 dots button. We specify where we want to save this file, and we give it a name. So I have already ROI.shape, so I will just overwrite this file, but you can save it as just, it's enough to type ROI. You don't have to put .shp because it will be assigned by default. So just ROI, save. Then next we should define geometry type. And geometry type in this case is polygon. Next thing is defining coordinate reference system. By default, we have WGS84, but we want to change this into UTM zone 37N, because this is the coordinate reference system of all the other data that actually of our pre-processed satellite imagery. So we want to keep it consistent. So we select this one, EPSG 32637. And with this, we can click on OK to create a file. We don't need to change anything or to add anything else. So for me, it's asking if I want to overwrite the file because it was already existing in my computer, but probably if you are creating for the first time, you won't see this. Okay, so now that we have this ROI file, we it's just a file, but it doesn't have any features yet. So next thing that we are going to do is first we are going to define a couple of values that this vector file can have once when we create features. So it's, in other words, it's creating predefined values. And this is done by right-clicking on this empty layer. Right-click, and we go to the properties. Sorry. For some reason, I get Windows open on my second monitor. Okay, so then in the properties, we switch to the attributes form tab. In order to create these predefined values, we select ID in the available widgets. And then we should see this appearance as you can see here. The only thing that we should change here is the widget type, and widget type should be value map. And then we insert which values we want to define. In our case, it will be value 1 and 2 for built up and non-built up respectively. So the first thing that I'm going to do is to double click on this field here for the value, and I will insert 1. Then I will double click on the description in the description cell in the row 1. And I will type here the non-built up. Non-built up. So basically what we did here is we defined which numerical value we want and what is the label for this numerical value. And we will do the same for the second class that we are aiming at. It's 2 for built up class. Okay, so that's all. We can now just click on OK, and this part is finished, but a bit later we will see what we created right now. Okay, so Professor, you can continue now.
Okay, so thank you, Goritza. And just to summarize what we saw now we are creating the structure for the file, because before we had only the name of the file and the main characteristic like the reference system and so on. On the opposite, now we want to create the structure of the file, and specifically we say that we have the polygons, and we want to attribute to these polygons the two values, 1 for non-built up, 2 for built up. So in this case, this is a property of the file, and therefore, as Goritza showed us, if we want to create the structure, we will select right-click on the name of the file and selecting properties. And at this point, as Goritza showed already, we select the attribute form, and what we wanted to define is the value ID for the two different classes that we are considering. As a widget type, this is a value map, so you selected value map, and then you entered in this menu where you put exactly what is written here. So the value 1 corresponds to non-built up, the value 2 corresponds to built up. Once you did this one, you clicked on OK, and now the structure of the file is completed. Now we have to create it, to create the polygons. So how it is possible to create the polygons. For creating this polygon, we need to have a background, obviously. We need to have something helping us in seeing where we have non-built up and where we have built up. So one possibility with QGIS is to use some images that are available as background. For doing that, as those images are available as services, and the services are provided via the web, what we have to select in the main menu is web. So we select web. We already installed the plugin, which is Quick Map Services, and therefore under web we find Quick Map Services, and then there is this list of all possible services appearing. Among them, what we want to select now with you is Bing, and opening Bing, we see that we have again more possibilities, the map.ru, or the Bing satellite. And what we want you to ask is to select the Bing satellite. So web, quick map service, Bing satellite. It could be that in your installation of the Quick Map services, the Bing satellite is not available. So if you are in this case, Web Quick Map services, and you have a shorter list with respect to what I showed you before, it means that it is not complete, the list of the available services. So at this point, you go to settings, you select settings, and then there is this window opening. In this window, you select more services and get contributed pack. Once you click on get contributed pack, you save it. And then at this point, you have available all the possible services providing you maps and images. So at this point, you go back and as we saw before, you select the Bing satellite. Okay, so now we are in this condition in which we have our area of interest, but besides our area of interest, we have also the Bing image showing what is the word in the region we are interested to work. So at this point, we can really start working on creating the file of polygons. For doing that, we select the vector file, so the ROI file, and then at this point you see here in this menu, you see that there is a pencil. This pencil is the icon for the toggle editor tool. So we select it, and then close to it, you see another icon, which is the Add Polygon feature. It's a polygon here. It's represented a couple of polygons. And so we select also this one. So we want to add, we want to edit, and we want to edit specifically polygons. Okay, wonderful. So at this point, we are in the editing mode, and therefore, left-clicking, we can start drawing the polygon corresponding, for instance, in this case, of an area that is non-built up. You see that the part that I selected here is a non-built up. So I left-click, go ahead, draw all the vertices, and then right-clicking, I close the polygon. At this point, I will put here, we'll select here as ID, non-built up, and then I click on OK. I have created my first polygon. The built up is created exactly in the same way. So I find one part of the image where I have a built up, left clicking, I start drawing the polygon, right-clicking, I close the polygon. And so at that point, instead of selecting the non-built up, I will select the built up, and then I click on OK. So once we have all the polygons that we want to consider, at this point, we have to save our edits. So for saving our edits, very intuitive again, we have simply to select here this icon. And after selecting this icon, we will deactivate the editing, clicking again on this icon, the toggle editing button. And in this way, we have finished our file, and our file is ready then to be used. So now the floor is yours, Goritza.
Okay, thank you. So let us first see how we can activate the ping that we will use for as a reference to understand which data is in different positions. It does is what we see belonging to the built up or belonging to the non-built up. So to activate the ping, we go to the web menu, Quick Map Services, and then here we should see Bing, and there are 3 different types of Bing maps, and we want to select Bing satellite because this is a very high resolution satellite imagery provided by Bing. If you don't see this long list of the base maps, you can go to settings. And in the settings, sorry, okay, now it's here. So in the settings, we go to this tab, More Services, and we click on Get Contributed Pack in order to expand the list of available maps, because by default, they provide just maybe 5 or 6 maps, and then we can extend this. So we click on Get Contributed Pack. Okay, and we save. And now I will again go to activate the Bing because I didn't do it the first time. So Web, Quick Map Services, Bing, and Bing Satellite. Okay, now we need to switch off all the other layers except the Bing Satellite and our vector that we created for creating training data, the one that we called ROI. So I switch off the layers by unflagging this box next to them. So everything except the ROI that is created by us today and Bing Satellite. Now to add new features to our ROI vector, we first need to enter into the editing mode, and this is done by first selecting the ROI vector and then clicking on toggle editing this pencil icon. Then we click on this button that is Add Polygon Features in order to activate the possibility of adding new polygons in our map area. And finally, we just need to zoom in to some area. Zoom our map, you can scroll your mouse, for example, or use these tools for zooming that you can see here. I will simply zoom in by scrolling. And first, I zoomed in into an area that is non-built up. So here I can draw a polygon that will be a training data for non-built up class. And I draw a polygon by left clicking. So every time we left click, we create another vertex of a polygon. And once we are done with we want to stop creating polygon, or we finished creating polygon, we right click to conclude the editing of this specific polygon, not of vector, but this specific polygon. And when we right click, we will get this window because we predefined the values for this layer. So we will have the two predefined values, and we can select whether this is non-built up or built up. And of course, in this case, we will select non-built up. So this is how you create a single polygon. And then, of course, the procedure for creating a built-up polygon is the same. It's just the matter of searching for an area that contains built-up area. For example, here, we can see some houses. So I will start creating a polygon for built-up by left-clicking. So I'm creating first the vertices. And now by right clicking, and again I can select one of the two predefined values, and I will select built up, and okay. Now this is not enough for the training data, the two polygons that I just created, but in general, we need more, and as Professor Bravelli explained before, there are some rules to follow, but then the rules really depend on the type of classification that you are doing. So in any case, we will stop creating this training set right now by first saving the changes on this icon, Save Layer Edits, and then also exit from editing mode by clicking on the pencil. Okay, and we will not use the training data that we created right now, but the training data that I provided you. So the roy.shape that I provided you before, if you downloaded the data that we provided to you in advance. And I just want to mention that this training data that we provided to you, we provided them so that we all can obtain similar results. In this way, it will be clearer if we are doing things good or bad, but this training data is not something that is, let's say, good training data. So we created this only for the purpose of the training of the workshop. So when we are creating in general the training data, we need to have in mind which is the purpose of the classification. And in this case, like, we don't have really a purpose except for just showing, so we didn't provide the training data that have all the aspects that a good training data should have. So just keep this in mind. In any case, when you have to do your own classification, you will have to create different training data, and probably will not work also in the same training, in the same working area. So this training data should be fine for the scope of the workshop. And that's it from me.
Okay, so thank you so much, Gorza, also for the comment. And I saw that there were some questions in the chat. So first of all, it is obviously not mandatory of using the being image. It's just one possibility that is offered because we have available this image, which is an high resolution image. But if you have your own images, or if you bought your images, or if you have also your UAV images on everything that you have, you can you can also use these images, and in this case is also better. And generally, these images are raster data, and therefore you can add this layer exactly as we saw before in the previous lesson, and use this layer as layer for editing your sample, your training sample. With respect to the training set, it depends. It depends of it depends on the classification that you want to do. In this case, it is a very simplified case. As you see, we have in the image that we provided you, just for starting, you have only the ground, so non-built, as a matter of fact. So there is the desert and there is just a bit of vegetation and the buildings. These are the only things that you see in this image. But obviously, the more complicated is your image, the more classes you want to consider, and the more complicated will be your training set. So it means that having a very good training set is something that is very time consuming. And this is independent of the GIS that you want to use. So independently of the fact that you want to use QGIS like we are showing, or you want to use ArcGIS, it doesn't matter. The point is that creating the training sample in any case is something that requires time. And after that, I believe that we can have 15 minutes of break in such a way that people who have to finish this part can finish, the other people can relax. And so let us see again at in 15 minutes. Okay, bye now. Hello again. Welcome back for the second part. And before starting, I want to recall you that with respect to the training set, we are just showing an example again for better understanding the choice, the optimal choice of the polygons or points that you have to consider for training is much better if you look at one book related to remote sensing and specifically the classification. So in this case, we are just giving you an example, and obviously using the Bing image is not mandatory at all. You can use whichever source of information you want. The message is that the better is your training set, the better will be your classification. So we have to be very careful in selecting the set of the samples that we want to use for training the data, because the final classification depends strongly on how good is the training set. And after saying that, let's go to the second part where we will see how to make the supervised classification. Okay. So now we have the training set, and for doing the supervised classification, and specifically using the algorithm that I mentioned before, we will use the jetsaka plugin. As it is a plugin and we already installed it, what we have to do now is to go to plugins, to select jetsaka, which is already installed, and then to select the classification doc in such a way that the doc is appearing and we can work from that doc. The usage of the plugin is very simple. You will see appearing here the doc of jetsaka, and what we have to put here is, first of all, the image we want to classify, we want to use for the classification. And I recall you that the image is the image that we preprocessed last time, and that is called clip. Then as second point, we have to put here the training set, which is, I remember you, that is what we computed right now before the break, and is called ROI. And then we have to put here where to find the value for the classification. And the value for the classification was the ID. So 1 or 2, depending on the fact that we are considering built up or non-built up. Then at this point, once we have introduced this input, we have to tell the plugin which is the file of the output. So we will put here below the ID that we selected before, we will put here the name of the output, the folder and the name of the output. We will select this button, and selecting this button means that there is this window appearing where we can choose which is the classifier we want to use. And for instance, as first, we can start with the random forest, but again, I recalled you that we want to repeat the same procedure with random forest, the Gaussian Mixture Model, and the k-nearest neighbors. We are not using the support vector machines because it is not working well, so we are not using it. And as first, we will select the random forest. Once selected the random forest, at this point, we go here, and what we want to do in running the algorithm is also to create the error matrix. So as we are creating the error matrix, we want to save it. So select Save Matrix, and we will put here the folder and the name of the error matrix that we want to create. So in this case, we decided to call it error matrix underscore random forest. Obviously, this is up to you. We suggest you to use the same names we are using in such a way that then you can compare with our result. If there is something not working well, you can send us the file and so on. Then the last point that we want to introduce is the percentage of the data that we will use for training the model. And I will explain later what we mean, but as a matter of fact, what we want to do, starting from the training that we created before, is to split it into subsets. One subset will be used for training the model, and the other subset won't be used for training the model, so it will be left apart, and then it will be used for assessing the model, for seeing which is the quality of the model that we created. Then at this point, after that, we simply click on perform the classification, and then we are doing the classification and obtaining the result. After that, we can repeat it exactly the same way, obviously changing the name of the output files and the error matrix name in such a way to run the same data with a different algorithm, so specifically the Gaussian Mixture Model and the k-nearest neighbor. So all the input data are the same, and then we decide to save the matrix in the same way, 80%, all the same, but just changing the algorithm that we are using in such a way that we can compare the result that we obtain. And now, Gorica, is over to you.
Okay. So, thank you, Professor. So again, now that we have our region of interest, or actually the training data, and preprocessed satellite image, which is clip.tif, we can open jetsaka and classify this image using this training data. Before doing that, I will just remove this file that we created with only 2 polygons. So because it is definitely not enough for the training data. So I right click on it and click on remove layer, confirm, and it's gone. Okay. So first point here is to activate jetsaka, and we activate it from the plugins menu, jetsaka, classification doc. So plugins, jetsaka classification doc, and we should see here now the classification doc of jetsaka, where we need to define, first of all, the pre-processed satellite image. Second of all, the training dataset or training vector. And then the third point that we need to specify is which is the column of the vector file, or which is the attribute of the vector file that contains the classes in the training data. So in our case, the training dataset is roy.shape, and the column of it is ID, the only one, but sometimes you can have more than one, and one will be the key column. Okay. We have this. Now we need to specify which algorithm to use, and this is done by clicking on this button here. So I click here to open the settings where I can define what is the classifier. And we will select, out of the 4 available, we will select random forest. And that is the only setting that we will change. We can close this now. Then we need to define what is the output name and path, where we will save the output of the classification. So for doing that, we will click on 3 dots here to define a final destination of this file. And I will call it simply RF, which stands for random forest. And I will save it in my folder for output files. You are free to save it wherever you want. Okay, I give a name, I click on save. And that is fine. Then also what we want to do is to save the error matrix so that we can estimate how good was the classification, how accurate it was. And for that, we need to flag this save matrix field. And when we flag it, automatically the window will open where we specify a folder and a file name of the error matrix. So I will call it EM_RF, which is error matrix for random forest. This is the meaning of these letters. Again, I saved it in the folder that it's suitable for me. And then I click on save. And finally, we need to define how many points we want to keep for training and how many will be assigned to the cross-validation or assessment of the classification. So if we put 80% here, this means that 80% will be 80% of all these polygons. Sorry, display again. So 80% of the area of these polygons will be used for training, and the remaining 20% will be used for cross-validation. And with this, we are ready to run this model. And we click on perform the classification. Now just click on this and just wait. It will take approximately around 5 minutes, but don't try to push QGIS and to do other things because it might crash. So while we are waiting for this to be finished, I can just give you a very brief information about the algorithms that we proposed for today, because we don't have time to go into details. And yes, I can just quickly mention you some important points about different algorithms. And I strongly encourage you to check the links that we provided in the slides, because those links are specifically related to the algorithms that are implemented in jetsaka. I'm saying this because the algorithms might have variations depending on software in which they are implemented. So I provided specifically the links for the algorithms implemented in jetsaka. So the first algorithm we proposed is random forest. This algorithm is very famous, and this is exactly why we insisted to you to install scikit-learn so that we can use this algorithm. And of course, the reason behind its popularity is because it has great performance in different fields of application. So this algorithm is based on so-called decision trees, and this is why it has the forest part in its name, so random forest. Decision tree is another machine learning algorithm, and while decision trees themselves have some disadvantages, such as instability in case of small variations or variations in data, or overfitting or bias in the data, when multiple decision trees are combined in random forest, they constitute very robust machine learning algorithm. So I have to mention some relevant point about decision trees, as they are the main building blocks of random forest. So a decision tree works in such a way that it splits the data into multiple categories by learning what is called decision rules from the training data. So in a figurative language, a decision tree learns from training data, which are the key value of the attribute of the training data that puts one data instance into one class or into another class. And then when these decision rules are learned, they are applied to the new data for which we don't know the class yet. Now, back to the random forest and its name. We explained that the forest part of the name comes from the multiple decision trees used in the random forest, but we didn't explain why is it called random. So, so the random stands for random subset of data that is used for building each decision tree in the random forest. So each decision tree has some subset of data with which it works, and each data instance will be classified by multiple decision trees. And then at the end, random forest collects the results of each decision tree, and the class with most votes will become model prediction. So, and then number of trees in the random forest is usually something that can be tuned, but and optimal number is not something that is fixed. In case of jetsaka, the optimal number of trees is computed by jetsaka. Jetsaka has a way to compute this optimal number, but we don't have any control over it, so we cannot tune this parameter with jetsaka. Then if you want to implement random forest with Python or some other algorithm, you of course have this possibility. Okay. Then the second algorithm is the k nearest neighbors. This algorithm and the algorithms of similar type are called instance-based learning because they take the training data and they don't create a model, but they simply compare the new data, so the data that are supposed to be classified, with the training data. And then based on this comparison, the class of the new data is determined. Then the new data gets the label according to the label of majority of the neighbors of this new data instance. And finally, we can define with parameter k, which is in the name of this algorithm. So with the parameter k, we are defining how many neighbors of a data instance to take into consideration for understanding which is the classification of this new data instance. Again, in this case, optimal choice of the number of neighbors or the k value is highly data dependent. And in case of jetsaka, it is computed automatically. We don't have control over this. And the last algorithm that we proposed for today is Gaussian Mixture Model. So as its name says, this algorithm relies on the assumption that all the data are a mixture of multiple Gaussians. So when we provide training data to this model, it will split the data into clusters according to the class. So for the training, we know the classes, so the algorithm splits this training data into clusters, and each cluster represents one class. Then Gaussian distribution is estimated for each cluster based on mean, covariance, and the probability of this class, of the classes in general. And the dimension of the Gaussian distribution depends on the number of attributes of the input data. Then when we have new data for which we don't know the class yet, the Gaussian mixture model computes the probability that this new data, what is the probability that this new data belongs to each of the Gaussian distributions available in the model from the training data. And then based on this, it is the class is assigned, and this model is called soft classification because it computes the probability of belonging to each possible class that we have in the training data. But in general, we can at the end select only the class with the highest probability and then conclude the classification in this way. And okay, for me, the algorithm is still running. So usually it's done faster. So I hope it doesn't mean that my QGIS crashed, but I think we can launch a poll now to see what is the situation with participants if they manage to complete the to obtain the output of the random forest, and then we can, based on the answers, we can decide what to do next. So please answer if you obtained the output of the first classification, or your algorithm is still running, or you didn't even try to run the algorithm, just to understand where we are now and if we should proceed. Of course, I have the outputs ready, so in case that my QGIS is stuck, I can just restart it. So, okay, I see that about 1/3 is, so about 1/3 managed to obtain the results. So I think this is quite good, because also we will wait for a couple of more minutes. I mean, we can wait for a couple of more minutes, because now Professor will explain the part related to the validation, so we can keep our algorithm running in the background and hear what is next that Professor has to show us. So, Professor Bravelli. Professor Bravelli, are you there? I'm not sure now if I'm disconnected or I think Professor Bravelli is missing, so it could be that she has connection issues, which gives us some more time to complete the algorithm running. Thank you for your feedback about hearing me, because yes, now it's a bit, speaking like this, it's a bit difficult to understand if people hear you or don't hear you. Okay, thank you very much. So I hope that Professor Bravelli will reconnect soon. Oh, Professor Bravelli just wrote me that there was alarm in the building and she had to leave the building. I hope it's nothing serious. And I hope that you are patient enough to wait for her to come back. I will actually check the slides, but right now I don't have slides ready to show you.
I'm back, Gorica.
Okay.
Sorry, there was an alarm in the building and I had to go outside. Luckily, it was a false alarm, so nothing dangerous. So I'm back. Okay, let's start the sharing, and sorry for that, it happens. Okay, I hope you see my slide now. So probably did you finish the to run the classification tools?
Well, when I checked maybe 5 minutes ago, roughly 30% of people had algorithm ready. So I believe by now majority will have the algorithm.
Wonderful. Okay, so let us speak about a bit about validation. So first of all, I have to tell you that if you want to try it, there is also another plugin of QGIS helping us in validating the classified data. And the name of this plugin is this ACATMA. So it's a plugin for the accuracy assessment of thematic maps. And this is a plugin specifically conceived for doing the validation. So for deciding which is the best sample size for the sample for testing your data, so for validating your data, which is the sample allocation. It has also a user-friendly interface for the photo interpretation, because in case we wanted to make the validation, we needed to have very accurate data, and then it helps you also to calculate all the indexes that we need for the validation, so for the assessment of the accuracy of the classified data. But as this requires also a lot of time, we decided to skip it, and on the opposite, to show you simply how to do the internal validation, which is also called the cross-validation. So this is the reason why we consider the training set, and we divided it into the two subsets, one corresponding to the 80% and one corresponding to the 20%. Also in this case, 80 and 20 is not mandatory. You can decide also 90 and 10 is up to you, as a matter of fact, up to your experience. If you have no experience, a good percentage is this percentage of 80 and 20. Anyway, what is very important is to use one part of this set only for training the data, and one part only for validating the data. But on the opposite, so this is what we are showing you today, but on the opposite, if you wanted to really validate your data, meaning to validate your classified map using some external independent pieces of information, at this point there are some rules that you have to follow for creating also this testing set. And specifically speaking about the testing set, we needed to decide the size of the testing set, and we needed to decide also the spatial distribution of the testing set, so the allocation of the samples. And for doing that, we can follow some statistical rules, and specifically there is a formula that is given by Cochrane that allows you in computing which is the sample size. And generally, the value of this value, this size is around 400, a bit less than 400 samples. Or if you don't have this possibility, so 400 is too much, you have to deal with the less samples because of budget constraints. At this point, you know that your result is not so reliable as you have if you follow what is given by this statistical law. With respect to the allocation, so which is the optimal distribution of your testing sample, there are more criteria that can be adopted. The simplest one is to use the randomly distributed sample. So simply randomly extracting your sample and then using some high resolution imagery, or on the site checking which is the specific class in that point. Or there is another criterion, which is the criterion of the stratified random sampling, telling you that you have to consider the quantity of the different classes, so the surface corresponding to the different classes, and therefore doing, before subdividing the data in strata, considering the different classes, and randomly extracted inside these strata. And also in this case, the number of the samples can be defined accordingly with the strata size. So those are two possible criteria that can be used for determining the sample allocation. And then with respect to how to collect the data, again, the in situ collection, so in field, collecting in the field the data, or using very high resolution satellite imagery. Then at this point, let us see which are the tools that we can use for assessing the quality of our classification. The basic tool that is used is a tool that is called the error matrix. So we start with the error matrix, and we compute, starting from the error matrix, some indexes that are called the accuracy indexes. The error matrix specifically is a table, in this case 2 by 2, because we have only two classes that we are managing, where on the row we put the reference, it means the ground truth, what we consider as ground truth, and on the columns we put the prediction. So what is the output of our algorithm? So in our specific case, and I suppose this is the case of random forest, we have that our sample consists in 23,071 pixels. And if you look at this table, we have that for 19,309, the non-built for the prediction correspond to the non-built for the reference. So what we left out, the 20% that we left out and we didn't use for training our model. And the 3,821 of pixels, which derives from the classification, corresponds to what we have as ground truth. So it means that these two values are correct because the classification corresponds to what is the ground truth, what is the reference that we are considering. Okay, and on the opposite, the off diagonals are the values that are not correct. So are the wrong values. So starting from this table, this matrix, we can compute something that is called the overall accuracy, where the overall accuracy is nothing but the sum of the correct pixels for both the two classes divided by the total number of the pixels. So this is the overall accuracy that we obtained, which is 99.8%, so a very, very high accuracy. But this overall accuracy is saying nothing with respect to what happens for the single class. So what is the value that we have for the built up and not built up? So we don't know if one class is perfect and the other is wrong, or the two of them have more or less the same level of accuracy. For obtaining this value, we can consider other indexes that are the producer accuracy and the user accuracy. So the producer accuracy is the accuracy from the perspective of the producer. And mainly it answers to the question how many pixels of one class are correct. So for computing, for instance, the producer accuracy of the non-built-up class, we take the value that are classified as non-built, and we divide it by the number of pixels that are classified as non-built in the ground truth. So this is the classification, the result of the classification, and this is the ground truth. And in this way, we obtain the producer accuracy. On the opposite, the user accuracy is the accuracy from the perspective of the user, and it is computed considering the number of the pixel for one class, for instance, the non-built-up class is computed considering the number of pixels that are correctly classified as non-built-up with respect to the total number of the pixels that are classified as non-built-up. And so this is from the point of view of the user, this is from the point of view of the producer. And obviously these values can be different. So nothing say that these two values must be the same. They can be different. And these values are considered for checking, which is the accuracy that we reach, that in this case is very high because the maximum is 100%. Okay, so at this point, the other point that we wanted to show you is the intercomparison. Intercomparison is something slightly different with respect to the validation, because for validation, we need to have a sample, a testing sample, which is better than the data we have, which is better than the map we are classifying. So, for instance, in this case, in our case, we use the Sentinel-2 data with a resolution of 10 meters, and we consider the Bing images, which are higher resolution with respect to the 10 meters, in order to validate it. But if we want, on the opposite, to check how good is our data, our map, with respect to something which is similar in the size, in the pixel size. In this case, it is not a validation, obviously, because the two data can be considered more or less of the same level, and therefore, instead of calling it validation, we call it intercomparison. And this is something that generally we do with considering external pieces of information that are completely independent with respect to what we are using for our classification. So in this case, if we want to compare our data with an external source, which is more or less of the same accuracy, and it is completely independent, we can decide to use this layer, which is the Global Human Settlement Layer built, which is derived from Sentinel-1, so no more Sentinel-2 involved, and which is a product that is provided by the Joint Research Center of the European Commission. In this case, the specific coordinate reference system of this dataset is not what we saw previously, but is something different, and it is in WGS84 pseudo-Mercator. This is the EPSG corresponding to the coordinate reference system. So this dataset is completely independent with respect to what we saw now, because the satellite used for this computation is completely different, the procedure is completely different, and then at this point, we can compare the two data because they are completely independent of each other. Obviously, in the end, we can't say that one is correct, the other is wrong, but we can say where they are, where they are in agreement each other. Okay, so let us see the characteristics of our data, our classification output, and this GHS. So our classification output is given in this EPSG, so in this coordinate reference system. The resolution is 10 meters. It is just one tile, so we have one single file, and we have two classes, the class 1 non-built up and the class 2 built up. I wrote this one in red because pay attention that in your slide, this is wrong. It's written 0 non-built up and 1 built up. It is wrong. Please delete it and put 1 non-built up and 2 built up. On the opposite, the GHS is in the EPSG 3857, 20-meter resolution. It is divided in 4 tiles. So we have 4 rasters to be put together, to be merged together. And then we have that the null value corresponds to the non-built up and the 1 value corresponds to the built up. Okay, so we have to work on these files in such a way to make them coherent with respect to the reference system, with respect to the resolution, merging all the GHS in such a way to have a unique file, and changing the value of the classes in such a way to be able to compare them. Wonderful. Instead of repeating 3 times all the procedure with our 3 outputs from the 3 different classification that we did, we can use one tool that is the graphical modeler. Graphical modeler is very, very useful every time that we have to repeat many times the same procedure with different files, because we are building a model and then we can run this model created by the graphical modeler, simply putting a different name of the file and running in one shot, obtaining simply in one shot the result that we want. But obviously, for doing that, we need to create this graphical model. Okay, wonderful. So, as we are now in the domain of the processing, what we have to do for creating this model is to go to processing and select graphical modeler. Okay, so at this point, let us think about what we want to do. We have a file, first of all, we have a raster file, which is the output of our classification. And what we want to do, because we have the 2 classes, 1 and 2, on the opposite, here we have null and 1. So what we can do is to start from here and simply subtract the value 1 in such a way that we, in the end, have 0 as non-built up and 1 as built up. So 1 as built up here and 1 as built up here, 0 here and null here. Okay, so the first step is to use a raster calculator in such a way to subtract 1 to every value of our raster. Then if we go on the other side here, if we go on the other side, we have that the GHS is divided in 4 tiles. And so the first operation that we needed to do is to merge the tiles in such a way to have a unique file. Then at this point, as this is given in another reference system, we need to warp, so to reproject this file in such a way to make it in agreement with respect to the output, our output, which was coherent with the Sentinel 2. And at this point, what we can do is to clip this file that is larger in such a way to have exactly the same dimension of our classified data. the last point that we want to do, because I told you that in this GHS, we have the null value. Go back here, null corresponding to non-built up. What we can do is to substitute every value which is null with the value 0. So at this point, we have that the two files are completely homogeneous, and we can compare them. And for comparing them, we use another command that is called kappa. This is a command creating the error matrix and computing all the indexes that we already showed before, and also another index, which is an index called kappa. It is an index that the closer is to 1, the better is. Okay, so with this procedure, we are able of computing the error matrix, and then we can check the value of the error matrix to see how similar, how comparable are the two files together. So let us consider what we have to do. We said that we have to start the modular. At this point, once we start the modular as we saw before, so processing graphical modular, these windows open. And first of all, we give the model we are creating a name, like in this case, accuracy assessment, and we start saving it in such a way that we now have the empty model. Let's go ahead. What we want to do, the first thing that we want to do is to this step, the step of taking our raster file, using the raster calculator for subtracting 1 to every value. Okay, wonderful. So at this point, we are dealing with the raster layer. So we go here where there is the input. We select the raster layer because we are dealing with a raster layer. And we put here as a name, the classified raster, because we will use then for this input the rasters that we obtained from the classification. So from the random forest classification and the other classification. Once written here, the classified raster, we click on OK. Wonderful. And so we have the first, the beginning of our model. Then on the other side, the first step is to merge the different tiles of the GHS. In this case, we are not dealing only with one raster, but we are dealing with multiple inputs. And so in the inputs, we will select multiple inputs, and we will give to this generic file the name raster tiles, and the data type is raster because we know that they are 4 raster files. And then we click on OK. Wonderful. So at this point, what we have to do, we have the input that we need, the unique file corresponding to our classification and the 4 tiles corresponding to GHS. Now let's go ahead and subtract to the classified file the value -1. So what we need to do, now we want to process this data, so to use an algorithm. So we add an algorithm, and specifically the algorithm that we want to add is a raster calculator. So here we write raster calculator, we find the raster calculator here and we select it, and this window appears for doing the raster calculation. Okay, what we want to do is to take the classified raster and to subtract 1. So we will select a classified raster and we will write -1. Okay, then at this point, we open here this window and we say that what we want to work now, we want to work on the classified raster, and we click on OK. Now everything is ready and set, and we can click on OK, and we add the first step. So the procedure for computing a new raster independently then of the raster that we want to introduce, of computing the new raster with 0 and 1. Okay, now it's over to you, Goritza.
So, Professor, given that we have not so much time, should I proceed with showing, or it's better to...
Yes. Let's stay in this way. Let's stay in this way. Because I believe that now people have understood which is the logic of what we are doing. And so let's stay in this way, because in any case, they have available the slides.
Okay. So, yes, the first point here is to activate the graphical modeler, and that is done from the processing menu, graphical modeler, or there is a shortcut Control-Alt-G. And here we have a blank graphic model. First, we will define the name for this model, and we will save this model, and then we will add some element and then save again when we have a couple of elements. But okay, for now, we will define name here in the name field, and we will call it accuracy assessment. And saving...
Sorry, Goritza, they don't see the modeler.
They don't see the modeler.
No, we see only the main interface of QGIS.
Okay. I'm sorry, but I didn't understand. Zoom doesn't recognize this as a part of the QGIS. Okay. I think now it will be better because I shared a screen completely, not just one application. Okay, so again, I'm going to the processing graphical modeler. And as I said, we have to define the name. Is it better now? I mean, do you see now?
Yes.
Okay, so I will define the name accuracy assessment. And I will save this model by simply clicking on the save button. And I will give it some name. It can be, again, accuracy assessment. And then I click on save. I will avoid saving because I have this model already. So, but in any case, so this is the procedure to save it. Then following thing is to add what are the inputs for this model. And in our case, for like defining the inputs, we have to keep in mind which type of data we expect to use in our model. Otherwise, it's impossible. Or we can put all the possible type of data to account for all the possible, or we can just think of like approximately which kind of input data we will use in order to define appropriate input parameters. So in our case, on one side, we have classification output, which is just one raster. And on the other side, we have 4 tiles of another classified product. So we just have to know this. So our first input parameter will be just raster layer. And we can find input parameters here under the inputs in the lower left corner. I scroll up or down to find raster layer. I double click to insert it in the model, and I specify the name. We called this parameter classified layer, a classified raster. Okay, that's all. We give it a name and we click on OK. And then second input parameter will be actually multiple input because we have 4 tiles. And here, this one we will call, again, parameter name will be raster tiles. And we will specify that data type in this case is raster. We confirm by clicking on OK. And input data is now defined. Now, we will have some processing operation on both sides for the classified raster as well for the raster tiles. But let us first see now what is because we have less operations on the side of classified raster. So we will see what is the only operation actually for this input. And on the algorithms tab, we can see all the functions that can be used within graphical modeler. And here, usually by typing in the search box, we can find a function that is suitable for us. In this case, we will search for raster calculator. Oops. Calculator. And I will select the raster calculator, the one from raster analysis. There are multiple multiple providers of raster calculator, but this one is like the core functionality of QGIS, so I will use this one. Now, with the raster calculator, what we want to do is simply to convert values 1 and 2 into values 0 and 1. So just to reduce the values for value of 1. And it can be simply done by reducing 1 from the raster. So classified raster, we double click on classified raster to insert it in the expression. And then we insert minus by clicking on the minus in the operators. And we insert 1. And this is the expression based on which we will reduce initial values of 1 and 2 of this classified raster to 0 and 1. And this is because the raster to which we want to compare our raster has values 0 and 1, so we want them to be homogeneous with this regard. And also here we should just select reference layer so that extent, cell size, and coordinate reference system are automatically calculated based on this reference layer. So we just click on these 3 dots. We again select classified raster. We click on OK. And with this, that's all for the raster calculator. I click on OK. And now we have a new element in our model. Okay, I think that's for this part. Now, Professor will explain how to add the, sorry, I just zoomed out. Professor will explain how to add the, which are the processing operation for the second group of layers. Sorry, this can happen. Now my model is missing because I just zoomed out too much. Okay.
Okay, so thank you, Goritza. Let's go ahead with the 4 tiles and merging the 4 tiles. So we have the 4 tiles of the GHS. And at this point, what we want to do is to process them, merge them in a unique one. So again, we click on algorithm and we search the algorithm for merging. Among the algorithms that are available, there are more than one. We ask you, or if you want, you can do something different, obviously, but we are more familiar with this merge of GDAL. So we select GDAL and merge. Okay, at this point, there is this window which opens, and we go here, and in going here, we have, there is this, again, this window, new, and we select what is the general name of the raster that we want to process. And it is what Goetz created before, that is called the raster tiles. And then we click on OK. At this point, the only thing that we have to select here is that we want as data type, output data type, an integer, so integer 32. Once we have selected, so it means that it will be an integer, and so once we have selected this one, we click on OK, and then the procedure is ready. Okay, so next step, now we have the files, the tiles of the GIS, which are merged in one unique file. What we want to do now is to reproject it in such a way to be consistent with the classified file. So for doing that, we want to process the data. So again, we are dealing with algorithms, and we want to warp the data, to reproject the data. So algorithm, search for warping, and select the GDAL warp reproject. Okay, which is the input layer we are interested in. We want to put here the merged from the algorithm merge. So the file that we created before. Okay, and we want to reproject from the these EPSG, so the WGS84 pseudo-Mercator, to the coordinate reference system of our classified file, classified map, which is this one. Once we have selected this, we click on OK, and that's that. So it's ready. Okay, please pay attention that if instead of using the 3.10, that is the one that was considered for this workshop, you are using the version 3.16 of QGIS, which is now the long-term release, which was not the long-term release at the time we sent the first instructions. In this case, it is a bit different, but just a bit, because you have to select algorithm, warp reproject of GDAL, but then at this point, when you have to select which is the layer you want to consider for the reprojection, you need to go here to 1, 2, 3 and click here. And what you want to, you have more possibilities than before. And specifically in this case, we are using the output of the algorithm that we ran before. Okay, so we want to select one output of an algorithm, and specifically the merged that was obtained from the merge algorithm. Okay, you see, the only difference is here in this 1, 2, 3, where you have to select, and you will select the algorithm output in this case. Okay, wonderful. So at this point, we have a next step, and the next step is to clip this new file that we obtained from before merging and then reprojecting. We want to clip it for an extent that corresponds to the extent of our classified map. For doing that, we are dealing with the processing, so we select algorithm, and what we want to do is to clip a raster by extent. And so we select clip raster by extent of GDAL again. Again, we go here and we put which is the file we want to reproject. We want to clip, so the reprojected from the algorithm work reproject. And then we put here, which is the extension that we want to consider. So we want to clip the file considering as extent the extension of the classified raster. Once we have selected this, we click on OK, and that's that. Another piece of the model is built. The last point is to substitute the null value of the GHS with the 0 value. For doing that, we will use another function, and therefore we are using, we are again processing the data. So we are dealing with algorithm. So select algorithm, search for r.null. That means it's working on the null value of the raster data. In this case specifically, we are using a grass functionality. Okay, so select this r.null. Then at this point here, we use as input the file clipped from the previous algorithm. And then the other point here is which is the value we want to replace to the null value of the original file. And we want to replace it with the value 0. Okay, we write here 0, okay, and that's that. Wonderful. Now we have all the chain for the JHS and all the small chain also for our classified data. What we have to do, the next step, is to compute the error matrix and all the indexes. And we know that this is possible by using, again, another functionality that is called r.kappa. So again, this is an algorithm. We search for r.kappa in grass. Then we put here which are the two files that are involved in this comparison. And as first file, we have the output from the algorithm of the raster calculator. So our classified map that was changed in the value subtracting -1, subtracting 1. And then as second file, we will put here the null raster from the algorithm r.null. Wonderful. So those are the two input file, and then we put here which is the output of our algorithm, which is of our processing, which is error underscore matrix. So this is the name that we give, the general name that we give to this output. Once we have defined also this one, we can say, we can click on OK, and that's that. So at this point, all our chain is ready. So if we go back, you see that we started from the classifier raster. With the raster calculator, we computed the new raster with 0 and 1. Then we started with the tiles of GHS. We merged them, we reproject them, we clip them considering the extension of this file. We substitute the all the null value with 0, and now we compute the error matrix and all the indexes related to the error matrix. So now the model is ready. So over to you, Goritza.
Thank you. Okay, so let us add some more elements to this model. And this time we are going for a processing operation regarding the 4 GHS tiles. And the first processing operation will be merging the tiles, so creating one raster out of the 4 tiles that are available right now. Sorry, just a second. Okay, so we go to the Algorithms tab, and we type in the search bar, simply we type merge. And we will find under the GDAL raster miscellaneous, we will find merge. We double click on it, and then now we can define the parameters for this processing operation. So first of all, what we want to define is what are the input data for this operation. So we will click on these three dots, and we will select raster tiles, because raster tiles are for raster that we want to merge, actually parameter for raster that we want to merge. Okay, and the second thing is output data type. We want it to be integer number, so we select int 32. Nothing else will be changed here. If we want to have this raster that is merged as an output, we can put a name here, but in our case, we will not go for that. So we will just leave this empty because we don't want to save this merged raster. We will do some more processing and then later save some outputs. Okay. So merge is ready now. I will just position it in a different position. That seems better to me. Okay, then next operation is reprojection. So right now these tiles are in a different coordinate reference system with respect to the coordinate reference system of the classified raster. So we want to harmonize the two different data sets with respect to this. So we again go to the algorithms. We search for warp reproject. So it will be this one, warp reproject of GDAL. I double click on it to start defining the different parameters. So again, first thing is to define what is the input layer here. And now input layer here will be output layer of the parameter. So I open the drop-down menu. I select the merge from algorithm merge. And then I say what was the initial coordinate reference system. It was this one, pseudo Mercator, EPSG 3857. And I say I want to reproject to this EPSG 32637, that is UTM zone 37N. Okay, other than this, there are no nothing else to be changed here, except just to mention this once more. In case of QGIS 3.16, you will have to define here that you want to use algorithm outputs for the input parameter. We will have icon like this one, and then you select algorithm output. But I'm speaking about input layer parameters. Okay, so with this, I click on OK, and we have the next element. Next step is to clip the output of this operation to the extent of this file, because once when the raster tiles are merged, they are bigger than the area of our classified raster. So it extends computational time unnecessary, and so we will remove this additional area that is not needed for us. This is done again from the algorithms. We search for clip raster by extent. Again, this will be a function provided by GDAL, and we double click on it. We select input layer to be output of the warp. So it will be output from algorithm verb reproject. For the clipping extent, we will simply use the extent of this layer here. So we just select from the drop-down menu extent of the classified raster. We could use the raster output of the raster calculator as well. It will have the same extent, but okay. Extent of the classified raster. And that is all. We confirm this, click on OK. And now we see that we use information from this layer and this layer to compute a clip raster by extent. And final processing operation for raster tiles is replacing null values by 0. So we will do this with r.null. Again, in the algorithms, we are searching for r.null. And we double click once when we find it, we double click on it to open it. Okay. Again, as an input for this r.null, we are using the output of the previous processing. So it will be this one, clipped extent from algorithm clip raster by extent. And we put here 0 so that what is currently null values or no data value converts to 0 value. So I will put 0.0 to be a floating number, but even putting just 0 should be fine. So 0 as integer. Okay. Now preprocessing is complete, preprocessing part, and we just miss now the step in which we compare the two preprocessed dataset. And that is that will be done with r.kappa. So we will search for that in the algorithms, r.kappa. So we define for r.kappa, we have to say which is the raster layer that contains classification result, and for us it will be this one. So it's layer that contains classification result, but we did some processing of this layer to just to adjust it to the second layer. So we will put here output from algorithm raster calculator. Then raster layer containing reference classes will be preprocessed raster tiles or the output of the last processing operation. So r.null. So now raster from algorithm r.null. And here we will also enter the error matrix, with which we are specifying that we want to save the output of this operation. It will be saved. Okay. And now this algorithm is ready. Again, or maybe not. Yeah, again, we need to save it. We save changes. And then we can run the algorithm, but I think I'm now going ahead of what you explained, Professor, no?
Yes, but as it is just a matter of one command that the running of the algorithm, you can show what they have to click for running the algorithm, and that's that because we are late.
Okay, okay. So I will just repeat once more. We need to save the algorithm, and then by clicking on this button, we run it. And then here, as you can see, we don't have any element. These are just parameters that we have to fill with the real data so that we can obtain some results. And so as we said before, for the classified raster, we intended the output of the classification. So it will be the random forest RF file. For the raster tiles, we intended this to be 4 tiles of GHS. So we can select this 3 dots button, and we will select the four GHS tiles that are already open in QGIS, and that's why we can see them here. We click on OK. And finally, we just specify where to save the outputs of this graphical model. We can save it as a temporary file, but let's save it as a proper file. So we click on 3 dots, save file. And then I will call this error matrix. Let's call it error matrix 2 because we had already one error matrix. Okay, save. And then we can run this model to execute all the defined steps on the data that I specified right now. So we can use the same model with the different data if we want.
Okay, wonderful. So now you use it for the random forest, but obviously if you want to use with the other classified map, it's just a matter of running again this model that we created, putting simply another input instead of the input of the random forest. Okay, so I show very quickly the result that we got with the random forest, which is this one. Okay, so this is the model. This is what you saw with the Gaussian, and here we are, and those are the final results that we got. And as you see, as a matter of fact, the tool that we are using is similar to what we saw before. So again, the overall accuracy and so on and so on, even if in this case, we know that is not a validation, but an intercomparison. In any case, you see that the intercomparison between the result that we got from the random forest and the result that was obtained independently using other data, using another satellite and so on, is pretty good because we have an agreement which is more or less 86%. So this is a good result also for being satisfied with respect to the classification we did.
Sorry, Professor, if I can just add one thing.
Yes,
here.
please.
The result for the students will not be exactly the same as the one that we obtained, because if you remember, algorithm every time takes 80% of data randomly, so it will not take 80%.
The same 80%, yes.
So it will be slightly different. It shouldn't be very different from this, but if you look at the decimal numbers, like it will not match completely. Just this.
Yes, good, very good point. Exactly. Yes, because these 20% are randomly chosen. Okay, so wonderful. This is the conclusion of this workshop. I saw that there are some questions that were not answered, specifically when you are asking about reference books, papers. In case we will put some more about that available in such a way that if you are interested in deepening into these topics, you can do that. By now, we want just to thank you. I want, if possible, to see again all my students for thank them also. So Matilde, Francesco, Juan Pablo, Musa, Thomas, thank you a lot. Thank you a lot, Goritza, and again, thank you to Andrea and all friends in ITU, giving us this opportunity of teaching you how to use QGIS also for these advanced kind of processing. Thank you so much. And the word is back to Andrea.
I thank you very much, Maria. Thank you very much, Goritza, for this very, very interesting workshop. And thanks again also to all the students from the Politecnico di Milano, which assisted the participants in the QA and the chat. And big thanks also to all the participants for having attended this event in such a large number and with such an active participation. We really saw a very intense activity in the Q&A and in the chat. We are launching now a survey. We would appreciate your feedback to understand how much you liked today's seminar. We also encourage you to check out the AI for Good program online to see more sessions that may be of interest to you. For example, on May 13th at 16 Geneva time, we have a webinar on AI for heart attack prevention, the story of Iker Casillas, World Cup winning goalkeeper. We are pasting the links in the chat and I encourage you to join. With that, we have reached the end of this webinar and would like once again to thank everyone involved, our speakers, our participants, our partners, sponsors, and co-convener Switzerland. Thank you very much again and hope to see you soon again.
Rewind selector, rewind selector, rewind selector. Rewind selector, rewind selector, rewind selector.